Good morning, everybody. Let me start saying that please interrupt me at any time for questions. I will very much appreciate it that you make as many questions as you want. I think that will be helpful for everybody and perhaps especially for me. I have only 47 slides for the two lectures. Then I think that I can go slowly, we can go slowly, and you can interrupt me whenever you want. These two lectures, it's not working now. Okay. These two lectures deal with an estimation method that is called nested pseudo-likelihood estimation, both in the context of single agents, dynamic models, and dynamic games. The first lecture will be on single agent models, and the second part will be on dynamic games. In the previous lectures, we have seen two methods that are the most commonly used methods in the estimation of dynamic structural models, which are the nested fixed point algorithm applied to the calculation, the computation of the maximum likelihood estimator, and the two-step CCP method, or also called Hodge-Miller two-step methods. And the NPL estimator was proposed in my work with Pedro Mira in a paper in 2002 in the context of single agents. Later, we extended to the case of dynamic games. And it was proposed with the idea of trying to improve some computational aspects and also some statistical properties of the nested fixed point and of the two-step CCP method, okay? Then for the nested fixed point, our motivation was, well, one feature by definition of the nested fixed point is for every trial value of the structural parameters, we need to solve the dynamic programming problem. And often that means solving the dynamic programming problem a good number of times. And can we avoid having to solve the dynamic programming problem so many times? At the beginning, for our initial guess of the structural parameters, we might be very far away from the true values. Do we really need to spend so much time solving the dynamic programming problem in these first iterations? That was kind of the intuition, but it was not just our intuition, it was just a concern for everybody in this literature. No? The second type of motivation of our paper was related to the CCP method. And the CCP method computationally is very attractive, but in terms of statistical properties is inefficient. And is particularly inefficient in terms of finite sample properties. That is subject to a course of dimensionality. Okay, if we have a large state space, the initial estimates of the conditional choice probabilities is going to be very imprecise, and that is going to translate into imprecise bias estimates of the structural parameters. Okay, we have a state space with millions of possible states, but we have a sample with a few thousand observations. It's obvious that we are going to have some states where we never observe in our data. CCPs for these states will be completely noisy, and at the end, garbage in, garbage out. Okay, if we have very bad estimates of CCP, our estimate of structural parameters will be very bad. Okay, and these are the two issues that motivated our paper. Then the nested pseudo likelihood method shares common feature, builds clearly, strongly on both the nested fixed point and the two-step CCP method. Okay, as you will see, and it shares features with both of them, okay? Then similarly as the nested fixed point algorithm, and in contrast to the CCP method, it is a full solution method. What do I mean by a full solution method? It means that once we obtain this estimator, the nested pseudo likelihood estimator, we have a pair of structural parameters and CCPs that are a solution of the model. That is, the CCPs are a solution of the dynamic programming problem for our estimate of the structural parameters. Okay, we have this feature of this full solution type of method. Okay. Second, similarly again to nested fixed point and different to CCP, is it does not require us to initialize our algorithm with good estimates of the structural parameters. We can initialize with this algorithm with completely arbitrary values of the vector of CCPs. Okay. And third, upon convergence, and this upon convergence is going to be important, especially in the context of games, we are going to see that in the single agent models, we have that this nested pseudo likelihood provides the maximum likelihood estimator. Okay, it's not just that it's asymptotically equivalent. No, it's the maximum likelihood estimator. Okay, for a given sample. Okay, and the method shares this feature with nested fixed point. Now, similarly to CCP method, and in contrast to nested fixed point, an iteration of the nested pseudo likelihood method does not require solving the dynamic programming problem. Okay. In contrast, an iteration of the nested pseudo likelihood method requires the same type of computations as the implementation of the CCP method. Okay. When we do not have the finite dependence property. Okay. I'm going to distinguish, and it's going to be important to distinguish two different versions of the CCP method, one that follows the finite dependence property, another that doesn't. Okay. And without the finite dependence property, the computation of the CCP method requires to make some valuation exercise to obtain some values. Okay. And this valuation is similar, well, it's the same type of computation that we need for one iteration of the NPL. Okay, and one iteration of NPL has exactly the same cost as implementing once the CCP method. Okay, and what we are going to see that is in the context of single agent models, the nested pseudo likelihood is an alternative algorithm to nested fixed point to calculate exactly the same estimator, the maximum likelihood estimator. And what I'm going to claim here is that is generally a computationally more efficient algorithm in terms of computational cost. Okay, then the rest of the two lectures, I will talk first about single agent models and then about dynamic games. I will start with some notation, things that we have already seen in the other courses, but just to remind us about some important aspect of these models. And then I will spend some time in the policy iteration mapping, because the policy iteration mapping plays a crucial role in the nested pseudo likelihood. And I will spend some time talking about one property that in the context of single agent is very important. It's crucial for the NPL method, and it's the zero Jacobian property of the policy iteration mapping. Okay. Then once we saw these properties of the model, we will go to the estimation. I will define what is the nested pseudo likelihood method, and then we will see a particular algorithm that was the algorithm that was initially proposed in my work with Pedro to obtain this estimator, the nested pseudo likelihood. And then I will discuss computational properties and statistical properties of this estimator. Okay. Then for the second lecture, I will talk about dynamic games. Okay. And let's go with single agent models. Very similar notation as we have seen so far, perhaps a little bit different in some aspects, some Greek letters. Then time is discrete and indexed by t. As John explained in the first lecture of this course, basically what we have is an econometric model where there is a dependent variable y, some explanatory variables that we observe as researcher x in the vector x, and some unobservable variables for the researcher epsilon that are observable to the decision maker. Okay. Then I'm going to use y to represent the agent's decision, and y can take capital J plus 1 values from 0 to capital J. Okay. Then the agent takes this decision to maximize her expected and discounted flow of utility. I use beta to represent the discount factor. I will use pi to represent the payoff function or utility function. And I'm going to consider all the time that we are in a stationary model with infinite horizon and with primitives, utilities, and transition probabilities that do not change over time. Okay. Then a little bit more detail. Well, we are going to consider the model under the classical assumptions in RAS model. Okay. That is the conditional independent assumption and the additive separability of the unobservables. And we have here the additive separability of the unobservable. Okay. The model is completed with the transition probabilities of the state variables that we have the conditional independent assumption, or even a stronger version of the conditional independence assumption, that is the epsilons, the unobservables, are independently and identically distributed over time. And for concreteness, let me consider that we have type 1 extreme value, such that we have a specific expression for the integrated value function and for the choice probabilities. Okay. The x variables have finite support, and I use fx to represent the transition probabilities of the state variable x conditional on the action y, and I will use also capital F to represent the transition matrix of the state variable when the choice at period t is y. Okay. Then we have a dynamic programming problem that we can represent by Blackwell's theorem. Both the value function and the optimal decision rule in this stationary world are time invariant functions, and the solution to this value function can be obtained as the solution of this operator that is the Bellman equation and has this expression. Okay. And I'm going to use alpha to represent the optimal decision rule. Okay, then this is something that we have. Yep, please. Excellent question. There are some recent papers by Aureo de Paula, Christensen, and other co-authors that they have basically relaxed this assumption. They have non-additive separable epsilon, and they have developed similar results as the different results that Young developed for this framework in the context of non-additive and observables. And we lose definitely something, but it's possible. It's an assumption that is possible to relax to a certain extent. Yeah. Okay, more questions? Okay, then. As John Sitorsky mentioned, and then Bertel and Fedor, it's very convenient to make a reduction of the state space by using the integrated Bellman value function and the corresponding integrated Bellman equation instead of the original or the standard value function. Then let me use V sigma to represent the integrated value function. With logit and observable, we have this well-known expression for the integrated Bellman equation, where we have that is the logarithm of the sum of the exponentials of these conditional choice value functions that can be represented as today's utility plus the continuation value, the future expected utility. Okay, and we have also this conditional choice probability function with this logit expression. Okay, solution methods, as we have seen in previous lectures, to solve for a fixed point, for the unique fixed point of this Bellman equation, we can use iterations in the integrated Bellman equation, value function iterations. This converges slowly, linearly, but the complexity of each iteration is also linear in the dimension of the state space. Alternatively, we can use Polish iteration or Newton-Kantorowicz iteration that converts faster quadratically, but the complexity is between a square and cubic. Basically, the complexity is related to the inversion of a matrix with the same dimension as the dimension of the state space, and the complexity for matrix inversion is around, that is the number of basic operations that we should make to invert a matrix is something between quadratic and cubic. Okay, then I'm going to use this psi subindex theta to represent the policy iteration. Okay, this is a mapping that given a vector of choice probabilities for every action and every possible state, it gives us a new vector of choice probabilities. And a fixed point of this mapping is a solution to the dynamic programming problem. Okay, this mapping plays a very important role in the nested pseudo likelihood estimation. Okay, I'm using some index here for facility in writing some expression, but this subindex means that this is an argument. Theta, the vector of a structural parameter, is an argument in this policy iteration. Okay, if we change theta, we have a different policy iteration mapping, a different dynamic programming problem, and then we will have a different fixed point for this dynamic programming problem. Okay, and let me say a little bit more about this policy iteration or Newton-Kantorowicz mapping. Okay. Okay, P is the vector of all the choice probabilities for every possible action and every possible state, and it's a mapping from this vector, the space of this vector of choice probabilities, into itself. It's a contraction mapping for this class of model under conditional independent assumption, and additive separability is a contraction mapping. It has a unique fixed point, and it's a composition of two mappings. Okay, a mapping that we can call the policy evaluation mapping is what John described it in the first lecture as the V-greedy mapping. Okay, I'm going to call it policy evaluation mapping. It's a mapping that basically tells us if the agent behaves now and forever in the future according to this vector of choice probabilities, what is the vector of values for each possible state? That is the policy evaluation mapping. And the other mapping is the policy improvement mapping. This mapping tells us if this is the value, if you give me a value for the future, I'm going to obtain, that is, if I think that in the future the values of in each possible state is represented by this vector, I'm going to behave optimally today by making these choice probabilities. Okay, that is what the policy improvement mapping is. Okay, then the policy evaluation mapping is a mapping from choice probabilities into values, and it has this, in the model that we have here, it has this expression. Okay, the first part where we have this inverse matrix is this inverse matrix is evaluation matrix. This give me any vector of utilities, okay? I multiply this vector at each possible state. I multiply this vector by this matrix, and what I'm going to get is the present discounted expected value of these utilities, okay? That is what this valuation matrix does. And you can see that it depends on the choice probabilities, P, for every action Y, and on the matrix of transition probabilities, F of X. Here, this asterisk means the element by element or Hadamard product, okay? So element by element product. And then in the second expression in brackets, what we have is basically the expected utility, ex ante expected utility today of behaving according to the choice probabilities in P, okay? And this expected utility has two components, is the component that this pi vector, that is the expected utility that comes from the pi function, that is the deterministic part of the utility, the part that does not depend on epsilon. And the second, this gamma minus logarithm of P, is the expected value of epsilon conditional on epsilon, on that action being optimal. The expected value of epsilon 1 conditional on epsilon 1 being optimal, and so on, okay? And for the logic model, it has this expression, gamma minus the logarithm of the probability, where gamma is the Euler's constant, okay? Then this is the expression of the evaluation operator. You can see that the main computational cost here comes from inverting this matrix that has the same dimension as the number of state variables in the model, okay? Then the policy improvement mapping, that is, remember, the policy iteration mapping is the composition of this policy evaluation and the policy improvement. Give me a P, and I'm going to obtain this vector of values. And now, given this vector of values, I'm going to determine what are my optimal choice probabilities, okay? And it has, for the logic model, it has this very simple expression. I'm using here expression also in vector form. These are vectors of choice probabilities for every possible state, okay? Then basically the policy iteration mapping can be interpreted as the best response in a game where the agent plays against himself in the future, okay? That is, give me a vector of choice probabilities that myself in the future is going to play after today, okay? And then I best respond to that vector of choice probability to maximize my value today, okay? This is a thin intuitive interpretation of what is the policy improvement, the policy iteration or Newton-Kantorovich mapping, okay? Of course, in the equilibrium of this game, that is just the solution of the dynamic programming problem, myself in the future should behave exactly the same as myself today. That is, the vector of choice probabilities that are my best responses today should be the same as the choice probabilities of myself in the future, okay? An example that is important for the nested pseudo likelihood, because this is for the class of model where this method is particularly efficient computationally or has the main computational advantages, when the utility function is linear in the structural parameters, okay? Then by linear, what we mean is that the utility of choosing alternative Y given a state X is a vector of functions of Y and X, okay, multiplying the vector of structural parameters. This is a structure that, of course, is not completely general, but many empirical applications, they have this type of a structure, okay? Even if your model does not have this type of a structure, like a constant relative risk aversion utility function or things like that, you could approximate it with this, use this approach using a linear approximation of this around some initial case. But well, this is This is the particular structure that I'm considering here that is linear in parameters. Okay. When we have this linear in parameters utility function, and we have this logic model, the best response, the policy iteration mapping has this very simple, and I think that intuitive structure that is going to be super important for the implementation of the nested zero likelihood. Okay, and this is the psi theta policy iteration mapping for action y and state x. And basically, you can see that this is a logic model, a standard McFadden's logic model, okay, where the explanatory variables are this set tilde p and e tilde p, okay? And if we knew this set tilde p and e tilde p, this will be a standard McFadden's static. I would not like to call it static because there is a lot of dynamics there involved in these variables, but looks like a standard static multinomial choice model. Okay. And what is key is what are these set tilde p and e tilde p? Well, the set tilde p is the present value of this vector of explanatory variables. Okay. Given that I choose action y today, and we are in a state x today, okay? And you can see that the first component is this vector today, and the rest is basically a valuation operator applied to this vector of explanatory variable set, okay? Similarly for e tilde is a scalar, and is the present value of the future values of the epsilon, taking into account that the future realization of the epsilons, okay, the epsilon for a particular choice, of course, they are IID and they have mean zero. But in the future, the epsilon will not be, the realized epsilon will not be any epsilon, will be the epsilons that are optimal, okay? And therefore, the expected value of the future optimal epsilons is not zero. There is a selection, okay? Only the epsilons, the relatively better epsilons will have higher probability of being, or the alternative with higher values of epsilon will have higher probability to be choice, okay? And this is related to this gamma minus logarithm of p part of the utility, okay? That we need to take into account, and generally is an important part of this type of model. Okay. Okay, then very simple structure of this policy iteration mapping. You can see that given p, evaluating this mapping for different values of theta is trivial. Okay, once we have p fixed and we have calculated this set tilde and this e tilde, changing theta is as simple as evaluating the choice probabilities of a McFadden logic model. Okay, what is costly is given theta changing p. Okay, because that involves inverting this matrix, this valuation matrix that we have in this expression below. Okay, if we are changing p, we need to change the valuation. Okay, operator. Okay, and that will be the initial. But given p, changing theta is as simple as in McFadden's logic model. Okay. Yep. Why is costly? Sorry, can you repeat? Because you can see this expression. What is, okay, suppose that we have fixed p and we have calculated already set tilde and e tilde, okay? Now, and we have a particular value of theta, and then we have calculated these choice probabilities. Now you say, okay, instead of the theta that we have considered, suppose that we increase theta by certain amounts, okay? We change the value of theta. what is what we will have to do? Well, we will take the vector set tilde, multiplied by our new vector of parameter theta, do this for every choice alternative, calculate this exponential expression, calculate the denominator, and calculate these choice probabilities, as we would do in a standard McFadden static logic model. Okay? Instead, if we have a value of P and a value of theta, and you tell me, no, okay, I now want to evaluate this policy iteration mapping at a different value of P. What is what we should do? We need to evaluate set tilde and E tilde at a new value of P. If we go to the expression in the bottom here, that means that we need to change here. This is easy. This is just multiplication. Here. Most importantly, we need to change this matrix. This matrix is this matrix here, okay? And we have to calculate this new matrix with new P's and now make again the inversion. And this inversion, if we have 1 million states, is a matrix 1 million times 1 million that can be costly to invert. Okay. Thanks a lot for your question. Okay. Then this is the structure of the policy iteration mapping. Let me talk about one property that plays a key role for the properties of nested pseudo-likelihood estimate. Okay. First, we prove in proposition 1 of the paper in 2002 that this mapping is a contraction in this class of model. And then in proposition 2, we saw that in a fixed point, okay, if we are in a solution in the fixed point, because it's a contraction, it has a unique fixed point. Then if we are in the solution of the dynamic programming problem, if we are in this vector of CCPs that solve this fixed point mapping, the derivative of the evaluation mapping with respect to P is equals to 0. Okay? And this is, I think, quite intuitive if we think about what is this valuation operator. Basically, it gives us, for a vector of choice probabilities, what is the value, okay, for each possible state. And what is a property of the choice probabilities? The choice probabilities are optimal. The solution of this dynamic programming problem give us the optimal choice probabilities, the choice probabilities that maximize the value, okay? Then this zero Jacobian property says that at the optimal, we cannot change the choice probabilities of any choice alternative at any state such that we can improve the values. We are at the optimal, okay? Okay, then it's impossible to increase a little bit the probability of replacement in some states and reducing in others and increase the values. No, the values, we are maximizing the value at every possible state with the optimal choice probabilities, okay? Then derivative of the valuation operator with respect to P, this large Jacobian matrix, okay, at a fixed point is 0, okay? Now remember that the policy iteration operator psi is the composition of the valuation operator and the policy improvement operator, okay? Then the derivative of the policy iteration operator with respect to the choice probabilities is the product of these two matrices, these two Jacobian matrices. The derivative of the policy improvement, these logic probabilities with respect to V, times the derivative of the values, the valuation operator with respect to P. Because this is 0 at a fixed point, and this is bounded, okay? These are the derivative of choice probabilities, and basically by Williams-Daly-Zachary theorem, the theorem that John mentioned in the first lecture, these are just choice probabilities. This is a bounded value function. This Jacobian is bounded. Then we have something that is bounded times 0. This is 0. Okay. Then this is the 0 Jacobian property at the solution of the dynamic programming problem for theta, for given theta, we have that we cannot change, or marginal changes in the choice probabilities imply no changes in the best responses. Okay? In the policy iteration. Okay? And let's keep this in mind because it's going to play a very important role both in the computational properties and in the statistical properties of this estimator, of an estimator that I have not defined yet. Yes? Sure. That's exactly, yeah, the same intuition as the Bellman operator. It's also true that the Bellman operator in general for Markov decision problems is always a contraction. It's not true that the policy iteration operator for any class of Markov decision problems is a contraction. For this particular type of problems, for these dynamic discrete models under John's assumptions, it is a contraction. Okay. Yep. Yes. Excellent question. I perfectly understand that at this moment it looks like very obscure why this is going to be useful. Let me try to before I go to the estimation and to the definition of the NPL that I have not defined yet. Okay, let me give a little bit more, provide a little bit more detail about an implication of this zero Jacobian property that hopefully is going to help you. And if it doesn't, just please let me know. Okay. And this slide, the purpose of this slide is exactly that. Is trying to provide some initial intuition why this zero Jacobian property is going to be useful, okay, for estimation. Let's think in maximum likelihood estimation, okay? In maximum likelihood estimation, given our data, we have a likelihood function where we have the logarithm of these choice probabilities, this equilibrium choice probabilities p theta, okay? And if we use, for instance, BHHH, and basically any gradient-based optimization problem for maximization of this likelihood function, we will need to use the derivatives of these choice probabilities with respect to theta, okay? Now, let's look at the structure of the derivative of these choice probabilities with respect to theta, okay? Remember that P theta is a fixed point of the mapping psi, then this fixed point condition applies, okay? This condition here. Then we can apply the implicit function theorem, the derivative of an implicit function, to obtain the expression of the derivative of this vector of choice probability with respect to theta as a function of the derivatives of the Jacobians of the policy iteration mapping. Okay, then let's take the derivative with respect to theta, both in the left-hand side and the right-hand side of this fixed point condition. Okay, then what we have is that this vector of derivatives that will enter in our BHHH method, okay, for the maximization of the likelihood function. I have not done the different steps, but basically we have first, basically theta is affecting this expression in the right-hand side in two different ways. First is affecting the mapping itself. I don't know what happened, but that should be a detector or something. Okay, let's look at this particular expression of the operator. Then theta in a fixed it has two effects, or is affecting the is affecting this right-hand side in this fixed condition in two different ways, okay? First is the direct effect. Theta enters here, okay? And we have the partial derivative of phi with respect to theta is through this expression here. This will be, let me call it, a standard McFadden's type of derivatives, okay? Very simple closed form expression, okay? But we have also that in a fixed point, P depends on theta, and therefore we have to look at how this function psi depends on P. We have to take the derivative of this expression with respect to P, multiply by the derivative of P with respect to theta, okay? And that's what things become complicated. The derivative of psi with respect to P is quite complicated. Notice that P enters through this inverse, okay, matrix. We need to take the derivative of this inverse matrix with respect to P. This is going to be complicated, okay? Then, if we basically use this expression, we can write that the derivative of the equilibrium, let me call it equilibrium choice probability with respect to theta, in general is going to have this expression, is the identity matrix minus beta multiplying the Jacobian of the policy iteration mapping with respect to P. This is a very high dimensional matrix, the dimension of the state space, and a very complicated matrix, because here is where we have basically the derivative of this inverse with respect to P, okay? In principle, very complex matrix, okay? And then we have this, the inverse of this inverse multiplying the derivative of theta of the psi with respect to theta. This is very simple McFadden times of derivative, okay? What we are doing in the maximum likelihood estimation, if we are not taking into account that in the fixed point, basically these properties only be true at the fixed point. Then in the maximum likelihood estimation, because we are not, okay, in a fixed point, if we are not in a fixed point, then we are calculating all the time this type of matrix, okay? This can be very complicated, okay? Instead, if we know that we have in a fixed point, we have the zero Jacobian property, we know that this is zero. And therefore, what we have is that this derivative at a fixed point is just the McFadden's type of derivative, as simple as that, okay? Then this is going to facilitate very much this computationally, the implementation of the estimation, computationally. And then it's going to have also an important statistical property, okay? Is that a particular estimator that we are going to define is equivalent, is the same as the maximum likelihood estimator, okay? Okay, then so far, yes? Yes, pretty much. Yes. I think that this, I will relate this particular expression more to the envelope theorem. I think this is clearly related to the envelope theorem. The zero Jacobian property, I will interpret it more like the standard first order condition of optimality. At the optimal, the derivatives are zero, okay? And this is more like a envelope theorem implication of that first order condition. Yeah, excellent. I think that that's a useful analogy, okay? Okay, then so far, nothing about estimation. It's just the model, the policy iteration mapping, and some properties of the policy iteration mapping. And let's suppose that we have a sample, panel data of individuals over time, and individuals over t periods of time. We observe the actions and the vector of observable state variable x. And our purpose is to estimate the structural parameters of the model. Okay, this vector of parameters theta. Okay, then for the definition of the nested pseudo likelihood, it is important to define the following function. Is the pseudo likelihood function. Okay, and it's a function. My favorite, basically, to put it short, is a likelihood function where we do not have the equilibrium probabilities. We do not have the p thetas. What we have is that this policy iteration or best response function probabilities that of course depend on theta, but depends also on p. Okay. Then one possible interpretation of this pseudo likelihood function is that consider a model where we consider that players or agents have some beliefs about how they will behave in the future. Okay. And these beliefs can be represented by the vector of probabilities P. That is, we have like two sets of structural parameters, if you want, in this model. Okay, we have the structural parameters and the utility theta, and we have these structural parameters in the beliefs of the beliefs that an agent has about how I will behave in the future. Okay, and these new structural parameters are P. Okay, and then we construct a likelihood function that says, okay, the likelihood function is the prediction of our model about the probability that the agent takes a particular action, or the action that we observe in the data, given the state, and given our two sets of structural parameters, the ones in the payoff functions and the ones in beliefs. Okay, and we can interpret this likelihood function in this particular way. Okay, of course we might want to try to estimate theta and p together, but we are not going to get identification. Okay, then what this likelihood function is missing or is not taking into account? Well, it's not taking into account the assumption of our model that these beliefs are rational. Okay, that an agent knows that his behavior in the future will be the solution of the dynamic programming problem. That this P, this vector P, is not just an arbitrary vector of beliefs, is the vector of beliefs that solves the dynamic programming problem given theta. Okay? Then, taking into account this, then we could define the maximum likelihood estimator as a constrained maximum likelihood estimator, basically as the value of theta and p that maximizes this Q function, this pseudo likelihood, subject to the constraint that the vector p is a fixed point of psi for the vector of parameter theta. Okay, and that's a definition of the maximum likelihood estimator, and then we could construct a Lagrange function for the maximum likelihood estimation. Okay, maximize everything with respect to theta and p. Okay, okay. In the context of the, okay, let me say, remember the structure of the best response or the policy iteration function when we have this linear in parameters utility function. What is this policy iteration function? Is this just logit expression? Okay, and basically what we have here in this likelihood are logit probabilities. Or at least we have logit probabilities once we have calculated this Z tilde and E tilde. And give me a value of P, I make this, I obtain this matrix, I invert it, I make this multiplication, I obtain Z tilde and E tilde for every observation IT in the sample. this becomes data, all this Z tilde and E tilde, and now what I have is a standard likelihood function of a multinomial logic model. Okay? And that's the way that we can see this. For given P, this is a very simple standard multinomial logic or conditional logic McFadden's likelihood function. Okay? Okay. Then what is the definition of the NPL estimator? The NPL estimator is defined as a pair of theta and P that satisfies two conditions. Okay? The first condition is that given P hat, theta hat maximizes this pseudo likelihood function. Okay? And given P hat, basically we have this logic model and theta maximizes the likelihood of this logic model. Okay? And second, and very importantly, given theta, P is a solution, or P hat is a solution of the dynamic programming problem. Okay? Then the NPL estimator is defined as these two conditions. Is this in principle equivalent to maximum likelihood? No. We are going to see this in more detail in the context of the dynamic games. But let me say already here that in principle, this is not equivalent if we have the Lagrange problem here, okay, of maximizing this pseudo likelihood subject to the constraint. We will have first order condition with respect to theta, first order condition with respect to P, and first order condition with respect to the Lagrange multipliers. Okay, we will have all these first order conditions of optimality for the maximum likelihood estimate. These three sets of first order conditions, these Lagrangian conditions, okay, in general are not equivalent to this condition. Of course, the condition with respect to the Lagrange multiplier, yes, the Lagrange multiplier are the first order condition with respect to the constraint, then these are exactly the condition with respect to the Lagrange multipliers, okay? The first order condition with respect to theta in the maximum likelihood estimator, no, okay? Because theta affects this likelihood in the maximum likelihood through the direct effect, but also through the indirect effect that I mentioned before, okay? And in principle, they are not equivalent. What we have is that the zero Jacobian property implies that these two conditions and the conditions that define the maximum likelihood estimator, they are exactly the same conditions, okay? Then this is taking into account the Lagrange, the zero Jacobian property. These two conditions are equivalent to the conditions that define the maximum likelihood estimator, okay? But that we will not see this if we are not aware that we have this zero Jacobian property, okay? Sure, please.
Does that hold only at the optimum theta hat, or was it hold for any theta along the way?
It holds at every theta along the way. As long as we are in the fixed point, in the P that is the fixed point for that theta, it holds all along the way. That's very important. Otherwise, it will be more like a asymptotic property or something like that, or a property at the local property at the maximum. No, this is for every value theta. Okay. Okay. Then in proposition 3 in our paper, we saw that theta and P satisfies the conditions 1 and 2 of nested pseudo likelihood if and only if theta is a solution of the likelihood equations using the true likelihood. Okay. Then a solution of the true likelihood equations in maximum likelihood estimation is a solution if and only if theta and P satisfy the conditions of the nested pseudo. And in terms of a local optimum, NPL and maximum likelihood give us exactly the same estimate. Of course, we may have multiple NPL solutions that satisfy for the same reasons that we may have multiple solutions to the likelihood equation. In that case, the maximum likelihood estimator will be defined as the solution of the likelihood equations with the maximum value of the likelihood. Okay. Similarly, if we have multiple values of theta and p that satisfy these two conditions of the NPL estimator will be the one with the maximum value. Well, this second statement here says that if theta and p satisfies these two conditions and are the values with the maximum likelihood, then theta is the solution of the likelihood equation that gives us the maximum value of the true likelihood. And basically, put it together, these two expressions, what we have is that the two estimators are exactly the same estimator. Yeah. That's exactly correct. Yes. We have a sorry. What do you mean by an early stopping problem? Sorry. You can have something that is perfectly consistent. You can have something that even could be asymptotically equivalent because this condition perhaps holds locally or something like that, but not something that is numerically equivalent for any given sample to the maximum likelihood estimate. Okay, then this is the estimator. Okay, so far is algorithm-free definition. Okay, I have not talked yet about any algorithm. It's just we have this pseudo likelihood equation, and we have a value of theta and p that satisfies two conditions. Okay. Now, of course, the key is how do we compute this estimator? Okay. And then in our paper in 2002, proposed the following sequential iterative. It can be interpreted as a particular fixed point way of calculating the NPL estimate. Okay. And the title of the paper is Swapping the Nested Fixed Point Algorithm, because this algorithm, it has the flavor of swapping the inner and the outer algorithm of the nested fixed point. Remember that in the nested fixed point, what we have is in the outer algorithm, we have the maximization with respect to theta of the likelihood function. We have the BHHH iterations. Okay. These are cheap. Once we have solved the dynamic programming problem, these iterations are very cheap. Okay. In the inner algorithm, we have the solution of the dynamic programming problem. This is computationally costly. Okay. Then typically in the nested fixed point algorithm, we are doing not many outer iterations, okay? But we are doing many inner iterations, many fixed point iterations, because for every trial value of theta, we have to solve the dynamic problem, okay? And our intuition was, what if we have an algorithm that we can reverse basically the order of these two inner and outer algorithms? Let's put the maximization with respect to theta inside in the inner algorithm, and let's put the policy iteration, okay, the solution of the dynamic programming problem outside, okay? Such that at the end, we are solving the dynamic programming problem, but only at the end, once we have converged to our estimator. But for every trial value of theta, we are not solving any dynamic problem, okay? And that, in principle, could give us computational savings. Okay, and this is the intuition of this algorithm. Then let me describe it in more detail. We start the algorithm, in contrast to the two-step CCP estimator. We can initialize this algorithm with any arbitrary vector of choice probabilities. Okay. Which in practice can mean that our initial estimate, non-parametric estimate, could be completely crap, as they are in many empirical applications. but we should not care, okay? Because we can initialize this algorithm with any arbitrary initial values of choice probabilities. Then at any iteration n, we perform the following steps or tasks, okay? First, given P, we go here, we calculate this matrix, we invert here, we calculate this product, and we calculate then Z tilde and E tilde at every observation in our sample for that vector of choice probabilities P, okay? That's the first step in one NPL iteration, okay? And the computationally more intensive step, okay? Especially because the solution of a high system of linear equations, that's what basically that is, okay? Then now, given Z tilde and E tilde, we maximize the likelihood function, the conditional logic maximum likelihood with respect to theta, okay? Then step 2 is obtain theta at iteration n that maximizes this pseudo likelihood function. This is piece of cake. This is just a standard McFadden conditional logic model, as simple as that. Globally concave likelihood function, super easy, as John mentioned in the first lecture, as easy as estimating a linear regression model, okay? Basic, okay? Then no problem of local maxima or anything like that, okay? And then in step 3, given the new vector theta n, we make one iteration, okay, in the fixed point, okay? What does it mean? Well, this is in fact computationally very easy once we have calculated step 1. Step 3 is apparently complicated, but we have done all the tasks already in step 1. What step 3 is basically coming to this expression here. We have already calculated the Z tilde, okay? Now we have the estimate of theta, just plug it in here and obtain basically a new vector of choice probability that comes from this equation, evaluated at the previous P and in the new theta, okay? And that gives us the new vector of P's. Super simple. This is like as when you have estimated your conditional logic model and you say, what are the fitted values of the model? That's exactly what it is. Obtaining fitted values for every possible value of X and every possible value of Y, okay? Super simple computationally, okay? And then, as usual, we check for convergence, okay? If we reach convergence, that's the nested pseudo likelihood estimator. Otherwise, we go back to step 1, okay? And now we have to calculate again these Z tildes and E tildes, okay? For the new vector of choice probabilities, okay? Then you can see that we are making many, okay, of these iterations for the maximization of the pseudo likelihood with respect to Q, but hopefully we are making not many of these outer iterations to update the vector of choice probabilities, okay? And this is the nested pseudo likelihood algorithm, or nested pseudo likelihood fixed point algorithm, okay? Because at the end is a fixed point, okay? What is the computational cost? Well, the inner iteration, yes? Sure. Sorry? Oh, I haven't included here, but yes, we will have a convergence. This is the argmax, then yes, we will have a BHHH there. Or we could have even Newton-Raphson, because we have numerical derivatives here for the Hessian, very simple expression for the Hessian. Then we can use either BHHH or Newton-Raphson, and there will be some convergence criteria. Okay. And in this step 2, we iterate in theta up to convergence. Okay. And we want to do that because that's very easy. Okay. Then we iterate as much as possible. Okay.
And you actually think to me that when your estimate
Exactly. Conditional on P, we have a theta that is a function of P. Okay. Then we get a new P that is a function of the initial P, of the previous P, and the new theta. Okay. Okay, excellent question. And this is going to be very important, especially for dynamic games. Okay. Then this could be very easy. Okay, but it might never converge. Okay. Then which are the properties, the convergence properties of this algorithm in terms of the single agent model? Okay. For single agent models, this, okay, it might not be a contraction. There is not a proof as far as I know of the contraction property of this algorithm. Okay. But I don't know any case where this has not been converged in single agent models. Okay. I don't think that it's possible to prove that it's a contraction. Okay. But I think that it's going to be difficult to find that for the single agent is not a contraction. Okay. What is basically what we are doing here? Okay. Here, this expression is like a fixed point mapping where P or Pn minus 1 is entering in two different ways. Okay. Is entering, okay, directly through the way that the P enters in Z tilde and E tilde. Okay. It enters in the Polish iteration mapping. And it also, because this theta n depends on Pn minus 1. Okay. Then this first channel of the effect of P is a contraction. We know that the Polish iteration mapping is a contraction. Okay. And the way that P enters here in this way is a contraction. We also know that the effect of theta on psi is also a contraction. Okay. Because there is discounting, changes in theta. Okay. Also imply that basically they have the contraction property. Okay. Then the only thing that could make this not a contraction is that by changing P here, we can get very large changes in theta, basically, in the pseudo maximum likelihood estimation. That's the only way in which basically we might not get the contraction property. Okay. Through these basically small changes in P, they might generate very large changes in Z tilde and E tilde, and could generate very large changes in theta, okay, that invalidate the contraction property. Okay. But both psi is a contraction both with respect to P and with respect to theta. Okay. And it's basically the dependence of the maximum likelihood estimate, the pseudo maximum likelihood estimator with respect to P, what might invalidate basically the contraction. Okay. And I think that, at least I don't know any result that they have shown that there are some properties in the data generating process such that we could have this type of effects of P on theta that invalidate. Okay. Then convergence properties of this estimator in single agent models are very good. At least the empirical applications have not shown anything that invalidate the contraction property, or at least the local contraction property of this algorithm. Things will be very different once we move in games, because we are going to lose the contraction property of phi with respect to theta, with respect to P, with respect to everything. Okay. But not in single agent model. Okay. Okay. Okay, then very easy to compute the pseudo maximum likelihood estimator theta n as a function of P. the main cause comes from this updating of the Z tilde, okay? And it will depend on how many of these outer iterations we need, okay? To achieve the estimator, okay? Then the relationship between let me mention the relationship between, I have emphasized so far the relationship of the NPL to the maximum likelihood and to the nested fixed point. How does relate this to the two-step CCP or the Hodge-Miller estimator? And let me again mention that we can distinguish two different versions of the CCP estimator. One that exploits the finite dependence property, and one that does not exploit the finite dependence property. Then the one that does not exploit the finite dependence property, and we can have a GMM version and a likelihood version. Here I'm presenting the likelihood version, but basically the two-step estimator without finite dependence property and with a likelihood version is basically estimating P, obtaining non-parametric estimates of the vector of choice probabilities, plug them in here, okay, calculate these Z tildes and E tildes, and then maximize the likelihood with respect to theta, okay? What that is just one step of nested pseudo likelihood. And one step of nested pseudo likelihood, if you start with consistent non-parametric estimates of the vector of CCPs, is exactly the two-step CCP estimator. Okay. Then in that, how much time do I have, Fedor? Okay. Okay, like 15 minutes. Okay, thank you. Then in that sense, we can see also the nested pseudo likelihood as a sequential method to improve the finite sample properties of the two-step estimator. And there are several papers by Kasahara and Shimotsu and by other authors that they have explored this, how basically the two-step CCP estimator, because the course of dimensionality in non-parametric estimation in the first step can give us a two-step estimator that has very large mean square error in a small sample, either large variance or large bias or both, okay? And then Kasahara and Shimotsu show that by starting now not with arbitrary vector of choice probabilities, but by starting this nested pseudo likelihood in non-parametric estimates of the choice probabilities and iterating in this nested pseudo likelihood, not necessarily upon convergence, we can get estimator that has lower finite sample bias. Okay, and there is a paper by Kasahara and Shimotsu in Econometrica 2009 showing this type of results for single AM models. Okay, then this can be sometimes referred as K-step CCP estimators or K-step nested pseudo likelihood estimation. Okay, but in that case, are not necessarily a full solution method. That is not that we are going to iterate necessarily up to convergence. It's more a method that is the main purpose is to reduce the finite sample bias of the two-step CCP estimate. Okay. Okay. In the paper, we present also some numerical experiments, some Monte Carlo experiment. Let me talk briefly about them. The main purpose of these, initially the main purpose was, in fact, everything started the other way. We didn't have our asymptotic results, but we thought about this idea, and then we implemented the nested fixed point. We implemented this algorithm, and we saw that we got exactly the same thing, and we couldn't believe it. Okay, And then we started to investigate why, okay, we are getting this exactly the same numerical result when we use this algorithm instead of the nested fixed point algorithm, okay? And then that we didn't do the Monte Carlo to be sure that our asymptotic result or our theoretical results were correct, because that in fact was our starting point almost in this project, no? To see that we were getting the same results, okay? But we wanted to basically see something that our theoretical results don't tell us nothing about, is that how many iterations we need of the nested pseudo likelihood, and then how is the relative computational cost of NPL and nested fixed point, okay? Then, as almost everybody in this literature, when you need to try any estimator or method or anything, you use John's bus engine replacement model, okay, and data, okay? And that's what we did. We used the data basically to use as the DGP, the estimates of the parameters, the actual estimates of the parameters using the data, but then the whole exercise was using simulated data, okay? Then basically the exercise is to compare the computational cost of nested fixed point and NPL in the context of the estimation of the structural parameters of the bus engine replacement model. To be more precise, we didn't estimate by maximum likelihood the parameters, or by full maximum likelihood, the parameters in the transition probabilities of the state variables. We estimated them in a first step, and then the purpose is the estimation of the parameters in the utility function, okay? And then we run these experiments for different sample sizes, 1,000, 5,000, 10,000, for different state spaces, 10, 200, 400, 800, 1600. And importantly, for different number of parameters. We fix some of the parameters. We consider also versions of John's model where he considered richer parametric specifications of the utility function, of the maintenance cost. And we consider versions with 1 parameter, 2 parameters, 3 and 4 parameters. All the time, we are assuming that the researcher knows the discount factor beta, okay? Then basically, even for the relatively small state spaces with 100 or 200, the ratio between the CPU time, the computational time of the NPL and the nested fixed point is basically exactly the same as the number of times that we need to evaluate, we need to make an evaluation of the policy iteration of the estimator with respect to P, okay? Basically, how many times we need to invert this matrix, okay? Oh, by the way, I have not mentioned, but as you have learned, we have different versions of the nested fixed point, depending on whether in the inner algorithm we use value function iterations or policy function iterations, or a hybrid of the two, okay? Because our nested pseudo likelihood is closely related to policy iterations, we are considering the version of nested fixed point that uses all the time policy iteration, that is Newton-Kantorovich iteration in the inner algorithm, okay? And that's what we are comparing, not the hybrid. The hybrid will do better. I think that the main difference will be that the hybrid might reduce in 1 or 2 policy iterations. That is our experience here, but no much more than that, okay? 1, 2 policy iteration for each inner iteration, okay? Okay, but that's what we did, is the policy iteration version of the nested fixed point algorithm, okay? Oops, sorry. Where we are, okay. Then the ratio of computational times of the two algorithm is basically the ratio between how many times our algorithm has to evaluate this matrix inversion for policy iteration versus how many times the nested fixed point has to do it, okay? The nested fixed point has to do it for every value of theta many times, okay? Up to convergence, okay? And then for every value of theta has to do it. Of course, it could be that we don't need many iteration in terms of theta for the outer, okay? In our case, we have to do this only in every outer iteration. In the inner iteration, the maximization of the likelihood with respect to theta, we don't have to make any of this matrix inversion, okay? Then what we got is that this ratio between the number of times that we need to evaluate this policy iteration operator in the two algorithms is super stable across sample sizes, perhaps not very surprising, very stable over different state spaces. The dimension of the state space, at least at this range, has very little effect on how many policy iterations we need, either for the nested pseudo likelihood or for the nested fixed point. Okay, if it has some increase in a way that the ratio remains pretty constant across the different state spaces. What is very important is how many parameters we have to estimate, okay? What is the dimension of theta? That has an important effect on the ratio, okay? And then in this experiment, what we get, this is the average time over we have for each of these DGPs, we consider 1,000 replications, okay, to have some idea of what is the average. Again, everything is very stable across the different Monte Carlo samples, okay? Then with one parameter, the nested fixed point needs 7 times as many policy iterations as NPL. With 2 parameters, this increases to 10. With 3 parameters, this increases to 13. With 4 parameters, this increases to 15, okay? And in this context, for this particular DGP, and basically the computational cost of the NPL is around 10 times faster than the nested fixed point, okay? In the context of these single agent models, okay? And the larger is the parameter space, according to our estimate, the larger is going to be this ratio. Basically, our intuition is that the search over the space of theta for the nested pseudo likelihood is going to require many more outer iterations when we increase the number of parameters theta. That is going to happen also in our inner algorithm, but our inner algorithm doesn't matter basically in terms of computational cost. It's negligible relative to the other tasks. Okay. Okay, and that's it for single agent dynamic models. Any question? Okay. Yeah, please.
So yesterday, Abby was talking about a dynamic equilibrium where you have a setting excess demand equal to 0 using Newton's method, and then inside you have to follow all these dynamic programming. Would you conjecture that NPL could be used to speed? So that's kind of a doubly nested fixed point. Do you think the NPL could apply to that problem as well?
I think that it could. These nice properties of the single agent models, we are going to see later that they not translate all of them to the case of dynamic games. Then I think that the issues that we are going to see later in terms of dynamic games will appear in that context as well, because we are not going to have a contraction, and we are not going to have the 0 Jacobian property in that case.
Okay.
Mm-hmm.
Thank you.
You're welcome. Yes.
The number of NPL iterations is approximately equal to the number of policy iterations. But I want to know whether it is theoretically guaranteed or not.
Unfortunately, we don't have any result about that. That's the reason why it could be either way, and it will not be surprising at all that there may be situations where the nested pseudo likelihood at the end requires many outer iteration, such that we end up having more policy evaluations than the nested fixed one. This is not at all a general property of the two algorithm. Okay. I have seen this. There are other exercises doing the same with other type of models, model of market entry and exit, and relatively simple models. We find typically this type of results, but I will never claim that this is a general theoretical property, not at all. No. Thank you. Okay. Okay, let's